as Greg just mentioned, I'm a recent grad of Penn State agronomy, and so I just moved to the Columbus area to work with Kevin. My previous work was mostly in nitrogen management from dairy manure, and so I've shifted now to start looking at soil test phosphorus and bring some soils perspective into the research lab with a bunch of engineers. So I will be sharing some preliminary work that I've been doing on looking at soil test phosphorus. And as Kevin mentioned previously with the TriState recommendations, we've been trying to figure out where our soil test phosphorus stands and how it relates to the DRP concentrations or dissolved reactive phosphorus concentrations coming off of our edge of field sites. And this is kind of a large, busy graph, but you can see we have it broken down by season. So spring, as the TriState just defines it, is March through July, and then water year, October through September on the right-hand side. And we have DRP, or dissolved reactive phosphorus concentrations, on the top, and we have loading on the bottom. And if we click through, we can see what our recommended loads are supposed to be. As Kevin mentioned previously, 0.05 for DRP for both spring and the water year, and then for loading a little bit higher for the water year, 0.29, and 0.11 for the spring season. And you can see a lot of our fields actually do fall underneath these recommended guidelines. Again, this is Malick soil test concentrations for 0 to 8 inches or 0 to 20 centimeters. So we're doing a pretty good job, but there's still some fields that are above, well above the threshold. So I'll take us through some of the work that I've been doing now, trying to dive into this and look a little bit more closely at the soils. So this fall, we were able to get into the fields before implementation of some of these practices that Kevin mentioned. And so I decided that I wanted to look at meter deep cores. So the picture below is us using a Giddings rig to look at soil concentrations at depth, not just the 0 to 20 centimeters. So we're taking agronomic quote samples at all these locations. And then we're also taking cores for stratification. And so I want to introduce some nitrogen analysis into this as well as phosphorus. I know the big focus is phosphorus with a lake, but I'm also interested in working some more on the nitrogen data. How are these practices influencing both of the nutrients that we care about in these systems? And so how do we assess it? Why does it matter? Basically, stratification is important because if we have, previous research has shown, if we have really high concentrations in those top 1 or 2 inches of our soil, that can result in increased losses in our surface runoff. These are predominantly tile-driven, tile-drained fields, as Kevin mentioned, and so does this relationship exist in our sites as well? Do we have high concentrations in surface runoff? How is it influencing our tile loads, et cetera? And so if we look at all of our fields, all 40 fields, and we look at average soil test phosphorus, we find that that top inch of soil is 65% greater than the weighted average of 0 to 20 centimeters or 0 to 8 inches. So you can see that that top portion of the soil is definitely driving the concentration for the agronomic sample. And so when we assess it, we're taking, you can see like a soil probe at the bottom, and we're cutting up the 0 to 8 inch core in the field and separating out and then analyzing each chunk, which a farmer wouldn't do, but from an environmental standpoint, we're interested in looking at. Okay. And so if we look at our soil test data overall, it's another box and whisker plot. We've got Malick 3 concentration on the y-axis, and then I have depth broken down on the x-axis in centimeters. So we got 0 to 2.5, 2.5 to 5, 5 to 10, 10 to 20, and then we're also looking at depth to 40 centimeters. And so you can see we've got a scale of 0 to 400 Malick 3P on the y-axis. We've got a few fields that are really high soil test, but the majority of our data falls in the 0 to 100 plus 150 range. And so I wanted to focus for this presentation on our data that is in that 0 to 100, 0 to 150 range. And you can see The bars are the median, and this is, as Kevin mentioned, 25th and 75th percentiles. And then these dots actually just represent some outline data. So you can see what you'd expect, like higher concentrations, the higher up in the soil profile, and as with depth, it's significantly decreasing. So nothing surprising there. But to drive home kind of that relationship between the top inch of the soil and then the deeper 8-inch profile, I just ran a quick regression to look at the data, and again, you can see there's a strong R-square of 0.8. We have the 0 to 2.5 concentration down here, and then we have 0 to 8 on the y-axis, and we have a pretty clean relationship between the two soil test concentrations. So just wanted to show that. And then moving into some dissolved reactive phosphorus concentration work. So again, we're looking at the top portion of the soil, the top inch, and then looking at the concentrations of dissolved reactive phosphorus coming off of all of these sites. And you can see, again, there's a fairly strong relationship. I mean, 0.38 R-square isn't super high, but we can see that there's definitely a trend. So with tile, and again, this is tile dissolved reactive phosphorus. In these tile-driven systems, we do see that top portion of our soil can actually influence what's coming out the bottom in these systems. And I guess another thing to mention, in addition to surface runoff increases, there's also been work done by Shipatello and others where in no-till systems there's a lot of macropore development, which is not necessarily a bad thing, but can sometimes create preferential flow channels. So that's why it's also an interest to look at some of these systems in reduced till or no-till, what is moving from the surface down to our tiles and out the edge of field. And again, so a similar relationship if we look at the 0 to 8 inch or 0 to 20 centimeter profile and we regress that against our concentrations coming out of our tile, we see a very similar relationship to when we just look at that top inch. So again, the relationship between the top inch driving kind of what's happening maybe throughout the soil profile. And to look, I know it's probably a little bit boring to everybody, a bunch of graphs, but bear with me. So basically, if you break the data down by depth, so here I have everything in the 0 to 2.5 all the way down to 40 centimeters, and you look at the relationship of the just overall malic soil test phosphorus and DRP concentrations in tile, you can see fairly high concentrations in the upper portions of the soil and then decreasing. The blue line is at depth, so we see that trend that we would expect. But basically when there's different slopes of our lines, then that means that there's stratification. If there wasn't stratification, we'd all have parallel lines and there wouldn't be any changes with depth. But trying to look at, okay, how is stratification influencing what we're getting out of our tile? And again, this is preliminary. But then looking at surface, we see similar relationships, but there's a constant. So this is looking at concentrations and not loads, and you can see that the scale changes. So we are getting the higher concentrations in surface runoff than tile, but generally, as Kevin mentioned, loading is more important in these systems in terms of more water is leaving the field in tile than an overland or surface flow. So trying to figure out how the malic 3 phosphorus in the top couple inches is influencing surface. Typically, the relationship has been stronger, actually, with tile than with surface runoff, where previous work has shown surface runoff concentrations of DRP are stronger with increasing soil test phosphorus. So I'm finding that there's a stronger relationship with what we're measuring from our tile than what we're measuring off the surface. And so this is kind of a new thing that I'm trying and moving into trying to figure out, throwing all the data. This is including all of our outliers, so you can see the scale on the bottom is 0 to 400. So looking at, is there a change in slope in our data? And that means when there's a change in slope, do we see a relationship with soil test phosphorus as it's increasing and the concentrations and loads coming off our field? And so I throw it into a model, and it's looking for any time that the data shifts. And so when I threw all of the data into the model, it was telling me that at 111 parts per million, or Malick 3P, there's a change in slope, meaning after that, then we're going to see an increase in DRP coming off our field. Well, that kind of makes sense. Those are really high soil test values. But if you take some of those outliers out of the data and then run the same model again, I find that around 29 soil test phosphorus, there's until 29, there's maybe a decrease in dissolved reactive phosphorus coming off the field relative to soil test phosphorus. And that's indicated by this kind of downward line. And then after soil test phosphorus, about 29 or 30, we see an increase. So maybe this is nothing new, but it's kind of promising to see that when you focus on our data that's in a certain range, it's kind of in a more realistic soil test phosphorus range, we see what we might expect, that anything above some of these agronomically important values, and we're going to see an increase in what's coming off of our fields. And so one of our collaborators who used to be in Indiana, Doug Smith, he was at ARS in West Lafayette. Before he moved down to Temple, Texas, he conducted a study where they wanted to look at phosphorus stratification specifically. And so they set up, you can see here, fertilized and unfertilized, different rates, different sources, so DAP, MAP, and then also different rotations. So looking at cover crop and then looking at placement. Like Kevin mentioned, placement is one of the big things we're trying to research. And so looking at injected and dist in. And so these were on the left-hand side of the treatments. And then on the right-hand side, you can see they did this in 2012. They did it on a corn-soybean rotation. Fertilizers applied in the spring. And then different fertilizers applied at different rates. And to look at phosphorus stratification specifically and runoff. And so, as he notes here, in 2014, great weather for growing corn, so that wasn't a variable in their yield. And so this is just evidence that not only does stratification impact what's coming off our field in tile and surface runoff, but it can influence clearly our yield and what we're growing. And so if you relate the Malick 3 phosphorus in the top, so they looked at 0 to 5 centimeters, and then below that they looked at the top 2 inches. There's no relationship between what you're measuring in your soil test phosphorus in those top 2 inches and your corn yield. So if you're in a no-till system, most fertilizers are going to be surface applied and not tilled in or not subsurface placed. And so that's not necessarily going to help your yield or predict your corn yield. So that was kind of an interesting thing to drive home, that what you're measuring, if you're just throwing your nutrients on your surface, your crop isn't necessarily going to reap the benefits. And so if you look at then the 5 to 20 centimeter depth, you can see that, again, we have Malick 3 on the x-axis, and then we have yield on the y. You can see there's a clear linear relationship between what we're measuring at depth versus your yield. And so surface applying is maybe the best spot if you want to lose, phosphorus off and surface runoff. But if we think his notes here are basically, if you think about where your roots are, the best place to be putting your phosphorus is where the plant can access it. So I think it's important to remember that not only do we care about what's coming off the field and our tile and our surface edge of field sites, but also how the crop is using it and how best we can think about managing for the bottom line and for yield benefit. So as Kevin mentioned before, placement is a big thing. Reducing fertilizer applications, perhaps. It's going to be a combination of everything. It's not necessarily one size fits all. And I think moving forward, it's interesting to look at how these relationships may or may not change with time. Like, that's the beauty of this project, is that we have paired treatments. We have farmers that are willing to work with us to look at alternative, quote, practices, maybe including subsurface placement. I previously did a lot of work with manure injection, so that's in a no-till system. And so, trying to prove to people that you can apply at the same rates potentially is also another thing. And I know a lot of dairy farmers cared about that. Can we subsurface apply at the same rate we're surface applying, for example? So working with people to prove that maybe this is something that's viable, that maybe it's not out of reach, is also important to consider. And just some conclusions. This is all preliminary. I'm still working on diving more into the data, but I think there's some promising results so far, and we're continuing to collect cores. So as treatments are rolled out, we have like baseline samples that we've collected before some of these strategies have been implemented, and then we continue to collect cores this spring and summer to see if we can monitor any changes. And looking at the stratification may not be agronomically important, but environmentally it's something to consider, because if we do have that top couple inches of soil driving a lot of the concentrations that we're measuring off these fields, then we need to consider how to manage that. And also not to forget the crop yield and crop rotation, some of the things that Kevin mentioned, like including small grains in our rotation or cover crops as a way to try and manage or mitigate some of the losses, are potential, I don't know, potential ways to manage a situation. And also it's legacy P. So if we're dealing with really high concentrations, previous concentrations, then how do we manage that moving forward?